Welcome. In this video, we'll be going over Class AB power amplifiers using bipolar transistors. So let's get started. As I mentioned, we're going to be looking at power amplifiers. And we'll be looking at Class AB. We'll assume that we've already seen the previous video, which looked at Class B amplifiers. So in this case, for Class AB, we want to have even when the output is 0 here, we'd like to have some current flowing from the N channel through the P channel, right from VDD or VCC to negative VCC. So right through the power supplies. And that keeps the N channel always on and the P channel always on. So we never allow them to turn off. So to do that, we've introduced two new voltages, Vbe over 2 here and Vbe over 2 here, which gives us a voltage always across here. So we have the equation that this current I sub n is equal to the current through the PNP transistor plus the load current. So it's equal to the current through the emitter of the PNP transistor and plus the load current. We also want to recall that if we know the VBE of the voltage across the transistor, that the current through the emitter is equal to the scale current divided by alpha. So normally we would show this as the collector current, and it would just be the scale current times e to the VBE over VT. But in this case, we have IS divided by alpha because we're looking at the emitter current, not the collector current here. So it's alpha is, if you recall, alpha is defined to be beta over beta plus 1. Then for power transistors, we'll find the beta is sometimes not 100. In fact, it could be 50, it could be as low as 20. So you'll sometimes have a much lower beta for power transistors. And we also have to recognize that power transistors are very large. So they'll consume a fair amount of area on a chip in order to deliver the kind of currents that we want to deliver into this load here, RL. We're assuming that's a fairly low impedance resistance, so that, and that's why we'll be driving a fairly large load current through here, and that's why we need large transistors. So as I mentioned, the emitter current can be given by this equation here. And we can reverse that and say, well, the base emitter voltage then is given by this equation. Just taking the inverse. When Vi equals V out and equals 0. So when this voltage here is equal to 0, and let's assume that we have matched devices. So our devices are matched. The NPN matches the PNP. Then we'll have the current going through the emitter equal to the current going through the the current going through the emitter of the NPN equal to the current going through the emitter of the PNP, and that will be equal to what we will define as the quiescent current. So as we mentioned, that's not going to be 0, and it's due to these two voltages that we have over here. And that's given by this equation here. And we can see this just because we've assumed that half of the voltage of Vbe over 2 is across the N MOS transistor. And so then using this equation with Vbe over 2 for Vbe, we have I sub n. And then the same would be true for the PNP transistor because we're assuming they're matched. So the goal when you're designing a Class AB amplifier then is to select that VBB in order to determine our quiescent current, I sub q. And that, as I mentioned, when the voltage then is equal to 0 at the output, both transistors will be on, and we'll have a quiescent current of I sub q going right through from VCC to negative VCC. Now when the input voltage goes greater than 0, then the output voltage is going to be the input voltage plus VBB over 2, since that's the top part, minus VBEN. So what we're saying here is when we increase VI greater than 0, this voltage here becomes VI plus VBB over 2, and this is VBEN here. So the output voltage is this voltage minus VBEN. That's what we have in this equation here. Now since we've already seen that the emitter current of the NPN equals the emitter current of the PNP plus the load current. And we also know that the base emitter voltage of the N equals the emitter base voltage of the PNP, and that equals VBB. So that equals the voltage from here to here, which will be VBB, since there's VBB over 2 here and VBB over 2 here. And so we've just added up these two voltages here. This is the VBE of N, and this will be the VEB of the PNP transistor. So what we see then, as the voltage VI is greater than 0, I of N will increase, the current through the NPN transistor will increase. That will increase the base emitter voltage on the NPN transistor. But since the two have to add up to a constant VBE voltage, the emitter base voltage of the PNP will go down, which means that the current through the PNP goes down. So we have what we had hoped for, that as this voltage goes up, this current increases, but this current actually decreases from the quiescent current. So it gets smaller than quiescent current, and we're delivering a lot more current into the load then. And the larger we make this, the smaller this one will become as it goes towards 0. And we've already started off fairly small because our quiescent current, we hopefully pick not too large of a quiescent current. We would pick it usually based upon the largest amount of current that we expect to drive. So some ratio of that. So now, combining this equation and the equation up above, this equation here, we can write out this equation. And then if we take the exponential of both sides, so if we take e to the left side and e to the right side, to get rid of the natural log terms, the 2 here, 2 term here will cause this to become squared and squared. And so we'll end up with this result here. It'll be this term multiplied by this term and this term squared due to that 2 term. And so we can then factor out the alpha s over the is divided by alpha parts, and we end up with this final result that the emitter current for the NPN transistor times the emitter current for the PNP transistor is always equal to the quiescent current squared. So if IN goes up, IP goes down, and it's always a constant. Of course, so that means if IN becomes very, very large, IP becomes very, very small, but it doesn't go all the way to 0. It just becomes 1 over IQ squared divided by IN. So we can then combine this equation here with the equation that we just found. And we can write out a relationship here, which basically will allow us to be able to find the emitter current for a given load current. So if we know what the quiescent current is, we know what the load current is, we can always find what the, using this quadratic equation here, we can always find the emitter current in the NPN transistor. So the benefit of this is that we no longer have our crossover distortion that we had before, but in fact the curve, if we plot Vi versus Vout, now looks more like a straight line going right through 0, and it maxes out at VCC minus the VCE and SAT, and the minus VCE plus VECP SAT. So we have a much more linear curve than we had in the class B case. So we would like to think about efficiency. How efficient are we compared to the Class B case? Well, it turns out the power relationships are almost exactly the same as the Class B case. So we really don't need to redo those at all. We just need to add a constant current of IQ to our results in the Class B. And normally we make our IQ fairly small so it doesn't change the results much at all. So if we had a 78% efficiency in the Class B, we might have a 77 or 76% efficiency in the Class AB. And it really depends upon how large we choose to make I sub Q. And we'll see some examples a little further on. The other thing we'd like to look at is the output resistance. So the output resistance is looking back into the output node, and we'll assume that our input is now grounded. So we've grounded our input over here. And we recall from a small signal model that our emitter resistances are just the thermal voltage divided by the emitter current. Thermal voltage is KT over Q, which is approximately 25 millivolts at room temperature. So the output impedance, looking back into that, is just going to be the emitter impedance looking up into the NPN transistor in parallel with the emitter resistance looking into the PNP transistor. So in parallel with R sub EP. And then we have that R sub En is Vt over In and Rep is Vt over Ip. Sorry. So we have finally that the output resistance is just the thermal voltage divided by the emitter current in the PNP transistor plus the emitter current in the NPN transistor. And so what we'll find then is, as we mentioned before, when In goes up, Ip goes down by the same amount. So we can see then that the largest output impedance will occur when Ip is equal to In, and that equals IQ. And in the case where the output voltage goes greater than 0, then In will become greater than IQ, but Ip becomes less than IQ, and we get an overall Rout decreasing. And the same would happen if we have Vout becoming less than 0. So if we want to look at for when the output impedance is the largest, we just look at the case when In equals Ip, which is equal to IQ. So let's do an example for a Class AB power amplifier. So in this example, we'll assume that our power supplies are plus 15 volts and minus 15 volts. We have VBB over 2 here and VBB over 2 here, as we normally have in our Class AB. We have the NPN transistor, the PNP transistor. Our load resistance will be 100 ohms. And we'd like to design this circuit. So we have a quiescent current of 2 milliamps. Given that our NPN and our PNP transistors each have an IS over alpha equal to 10 to the minus 13 amps, and we'll assume that the thermal voltage is equal to 25 millivolts in this case. And our goal will be to first off find the VBB voltage that we need in order to get the quiescent current of 2 milliamps. We'd also like to look at various output voltages and create a table that shows the output load current, the current through the NPN transistor, the current through the PNP transistor, the input voltage for that particular output voltage, the output impedance for that output voltage, and finally the small signal gain, which is defined as RL divided by RL plus R out for this amplifier, and see how much that changes as the output voltage changes. So first off, we want to find the VBB voltage. We had before that value or equation that gave us IQ in terms of VBB, and VBB divided by 2. We just rewrite that, and we can solve that VBB as 2 times the thermal voltage times the ln of IQ divided by IS over alpha. We're given all these values. This is given, and this is given. So we can just plug that into the equation. And we end up that VBB is equal to 1.186 volts. So VBB over 2, of course, is half of that. So that's the first part of the example. Second part is to look at various output voltages. So to find values for output voltages, we first choose an output voltage we want to look at. Then we can write that the output load current is just V out divided by RL, so it's straightforward. Now that we have I sub L, we have this value. I sub Q is known, so we can use this equation now to solve for I sub N. Once we have I sub N, we can also then use the equation here to find I sub P. I sub P will just be I sub N minus I sub L, or I sub P is equal to I sub Q squared divided by I sub N. Either one will work fine. Then we can use this equation to find the base emitter voltage. We need that because that is going to then be used to find our input voltage, because our input voltage is equal to the output voltage plus the base emitter voltage minus VBB over 2. In other words, if we know the voltage here, then we can find this voltage as summing together this VBE of this NPN transistor minus VBB over 2 here. So we can use this equation. Once we know the VBEN, we can use this equation to find VI. And R out we have from the equation before in the notes. So let's look at some of these numbers here. See that for V out equal to plus 10 volts, our load current, because remember the load resistance is given as 100 ohms. So if we have 10 volts as V out divided by 100 ohms, that equals 100 milliamps of current. So we're going to be plotting these values here. I sub L, I sub N, I sub P, and I sub N, I sub L, and I sub P, all in units of milliamps. So the first one we have is the I sub L is equal to 100 milliamps. I sub N, using the method we have above, is 100.04 milliamps. So it's a little bit higher than the load current because part of it goes through the PNP transistor. So I sub P is 0.04 milliamps. The input voltage is 10.1, even though our output voltage is 10. Again, that's just once we solve for VBEN. V out over VI large signal. So if we just look at the ratio of this output voltage to the actual input voltage, we see it's 0.99. our output resistance is equal to 0.25 ohms. And so if we plug that into this equation, RL is equal to RL plus Rout. So 0.25 ohms divided by 0.25 plus 100 ohms, we get a small signal gain of 100. Of 1. We get a small signal gain of 1. So even though the output voltage has a slight DC offset, if we put a small signal into it of, let's say, a 10 millivolts or something right on top of that, we'll have a small signal gain of 1. So it'll be pretty much equal to each other. Then we can reduce Vout. We get reduce the load current becomes 50 milliamps. I sub n becomes this. I sub p increases a little bit, not too much. The input voltage is now 5.008, and our small signal gain is still around 1. Finally, we can get a even smaller output voltage of 0.5 volts. In this case then, just clear those out. In this case, our output load current, I sub L, will be 5 milliamps. The NPN transistor is 5.7 milliamps, so fair, almost a little more than 10% current, more current than our I sub L. The PNP transistor now has 0.7 milliamps. VI is 0.526. So the ratio, again, the large signal ratio between Vout and VI is 0.95. But the small signal gain, if we look at the output impedance is 4 ohms. So the small signal gain is now 0.96. And finally, we can do the last case when the output is equal to 0 volts. IL is 0. IN equals 2 milliamps, which is the quiescent current. I sub P is 2 milliamps, which is the quiescent current. The input voltage will be 0. There's no point in looking at Vout over VI. 0 over 0 is undefined. And the output impedance is the largest in this case, so it's 6.25 ohms. And so the small signal gain is 0.96. So we see that our small signal gain goes from 0.94. So we see that the small signal gain goes from 0.94 to 1, so it only varies by about 6% over a very large swing from 0 volts to plus 10 volts. And we can see where that would make it a fairly linear power amplifier. So far we've talked about just putting in voltages at this node here, but now we want to talk about how to actually realize that VBB voltage. So we'll start off with, we'll say we're going to realize that VBB voltage, so how to bias it, and we'll use diodes for biasing this. So we put a diode here and a diode here. 2 diodes because we effectively have a diode here and a diode here for the 2 transistors. The VBE of the N channel and NPN transistor, and the VEB for the PNP transistor. Now we also would like to take into account this current here, which is the base current into the NPN transistor, and the base current I sub BP, which is the base current for the PNP transistor. And we have as before, I sub EN is this current, and I sub EP, the emitter current through the PNP transistor, is this shown here, and this is I sub L as before. So what we first notice is that I've changed where the location of the input voltage is. So rather than having the input voltage centered over here, if we did that, we wouldn't necessarily have any bias current going into the bottom diode. So instead, we've changed our input and put it down over into this region over here. So it's now to the lower side of both diodes. And we've added this current source here, I sub bias, which will supply the bias current going down through here. And so we have, what we notice then is V sub I has to supply potentially some current. There'll be some current I sub bias going down through here. So that some current is going to be flowing down through here depending upon what I sub BN is and I sub BP is. So we first noticed that V sub I has to source a current. Let me just get rid of some of these. So the current V sub I, the voltage V sub I has to source a current of I sub Vi. And that has to equal this current, I sub bias, subtract I sub Bn, and add together I sub Bp. So that's the current that we need to be able to source in our input voltage. We can't assume it's zero current as we normally would with MOSFET transistors. In the case where beta n is equal to beta p, we would see that I sub Bn would equal I sub Bp when the output voltage is equal to 0. And so in the case when the output voltage is 0, Vi would only have to source I sub bias in that case. Now, what we're going to look at is, assuming that we're using diodes to bias this, what we'd like to do is make the diodes over here some scaled version of the base emitter junctions for the NPN transistor and a scaled version of the base emitter junction for the PNP transistor. That would match this one over here. But what we're going to see is there's going to be an area penalty using diodes. And so we'll have to come up with perhaps a different way to do that. But let's look at why there's an area penalty if we just decide to use diodes. By the way, when I say to use diodes, the other possibility could be a diode connected transistor. So you could take one of these diodes here and use a transistor that's connected like this, and that would effectively operate as a diode. This would be equivalent to having this type of arrangement. Or they can be actual diodes. So we're going to define N to be the area of the base emitter junction for the transistor. So ABE is the for the NPN transistor. And A sub D is the area of the diode. And again, we're assuming that they're matched, so the NPN transistor and the PNP transistor both have the same area. So we've defined this ratio N, and we would like N to be much greater than 1 so that we don't have to use a large area for these diodes. Because remember, these transistors that we're building over here are power transistors. They're delivering hundreds of milliamps, and so they potentially are fairly large transistors. If we also have to build these just as large, just for biasing this, that seems like a waste of silicon area. So we would like our diode sizes to be much smaller than the sizes of the transistor. So we would like the N to be much greater than 1, which is the ratio of the area of the base emitter junction to the area of the diodes. So for V out equal to 0, in this case, we can look at I sub Q, so the current flowing down through here, is going to be equal to N times the bias current minus IQ divided by beta plus 1. And it's the equal to that value because it's N because of the ratio that we have, that the area of this is N times larger than the area of this. So the current through here will be N times the current through the diode. The current through the diode is I bias minus I sub Bn. So the current through the diode is given by I sub bias minus IQ divided by beta plus 1. The quiescent current divided by beta plus 1, which would be the base current through that transistor. If I multiply that by N, that should equal IQ, the quiescent current through that NPN transistor. We can rewrite that a little bit as this form over here. And then if we notice that this part here can be written as beta plus 2 over beta plus 1. So we end up with this equation here relating the quiescent current N and I bias and beta of the transistors. Recall that the beta of the transistors could be significantly less than 100. They could be down to 50, down to 20, because they're power transistors and their betas typically are smaller than 100. Now we also notice though that the bias current that we have has to be greater than the current that goes into the base of the transistor when we have the maximum current flowing through the transistor. So in other words, this bias current here must be greater than the maximum current that we ever have going into the base, and the maximum current that ever goes into the base is going to be the maximum current that we have coming down through I sub En divided by beta plus 1, because that's the base current. So we have that the bias current must be greater than the maximum current ever delivered by the NPN transistor divided by beta plus 1. And that's because I bias has to deliver that current. And if it's not, can't deliver that current, we can never deliver the output current. So if we combine this equation and this equation here, we see that N times the maximum current ever going through the NPN transistor divided by beta plus 1 has to be less than or equal to beta plus 2 times IQ. That implies that N, just multiplying through by beta plus 1, N times I sub E N maximum must be less than beta plus 2 times IQ. Now let's define a new parameter, K. K will be the ratio of our maximum current that we ever deliver through the NPN transistor divided by the quiescent current. So it's a ratio of the maximum current to the quiescent current. And this is normally a number you'd like to know. You typically don't want that to be extremely high, but if you make it too low, you're wasting power. Your quiescent current then is high, you'll get better linearity, but you'll burn more power. If you make it extremely low, you run the danger that first off, you'll get worse linearity because your output impedance and things will be changing more significantly. But you also have the problem that it may be more difficult to bias it, that any thermal gradient or other things that come into play could affect the bias currents. So with this new definition of K, we can take this equation here and rewrite it as this one here. Dividing through by I sub Q, we see that N must be always less than or equal to beta plus 2 divided by K. So what we now have is we have an equation that relates N, which is the ratio of the area of the diodes to the area of the transistors, between the beta of the transistors and the ratio of our maximum current to the quiescent current. So we can think of an example here. Let's say that beta was equal to 50. And let's say that we decided our maximum current relative to our quiescent current was also 50. So we would like to have only 2% of our maximum current ever being used as our quiescent current. If we did that, we'd see that this term here would be 1.04, so N would have to be less than 1.04. In other words, the diode areas would be the same size as QN and QP. So we would have diodes there just for biasing, basically the same size as our power transistors. And that would be a real waste of silicon area, doubling up our power amplifier stage. Now we should also mention thermal issues. That it's well known that in a bipolar transistor, if you get a rise in temperature, then you get a decrease in the VBE voltage. So if you fix the collector current, then your VBE drops by 2 millivolts for every degree Celsius that you increase in temperature. Or if your VBE is fixed, your collector current will increase as the temperature increases. So if I go and build a bias that has a fixed VBE, as my temperature increased, my collector current will increase, which will increase my power dissipation, which will increase the temperature, which will again increase my collector current. So I have the danger here of what's called thermal runaway. That if this is a positive feedback loop, and if the gains happen to be greater than 1, it could end up actually running away and getting hotter and hotter and hotter until the device becomes damaged. The way to get around that, and remember, these are power transistors. So power transistors are going to generate a lot of heat. If the power transistors generate a lot of heat, but the bias VBEs are in a position in the chip which is not getting very hot, then you're going to end up with the two not matching at all and having this potential for thermal runaway. But if you place your diodes close to where the output transistors are, the power transistors, so they're thermally close together, then as the temperature goes up, the VBE will drop and the IQ will remain roughly constant, which is a much better way to bias it. So the moral of this discussion is to say that you should certainly place your these bias diodes in thermal proximity to where these power transistors are. So as they heat up, they will also heat up the bias circuitry and keep things working together correctly. So let's do an example here and see the kind of numbers that we end up with. So again, we're going to assume that we're using diodes here. And we'll assume that our area of the diodes are 1/3 the area of the power transistors. So we have some savings here. So N is equal to 3. And we have our power supplies are going to be 15 volts. And as before, our load resistor will equal 100 ohms. And we'll assume that our output voltage is a maximum of 10 volts. So there's a peak amplitude of 10 volts, which is of sine omega t. And we also have, as before, our Qn and Qp have Is over alpha equal to 10 to the minus 13 amps. And we'll assume that beta is equal to 50. So we'd like to find I bias such that our minimum current that we ever get in our diodes is equal to 1 milliamp. Remember, in this circuit here, this will be a fixed value, but as I push more current, as IBN increases, this current is going to decrease. And I don't want it to ever get less than 1 milliamp. That's what we're saying in this example. So we want the minimum current through those diodes to be 1 milliamp. So that's our constraint, and we want to find the quiescent current that we can have, the power of the output transistors, so we can specify what output transistors to use, and find VBB for V out equal to 0, 10 volts, and minus 10 volts. Okay, so let's look at the solution for this example. So first, what we recognize is that we have our maximum current going through the NPN transistor will be 10 volts, which is our peak output voltage, divided by 100 ohms, which is our output load. So that's 100 milliamps. So we have 100 milliamps is the peak current flowing through here. We then also have we can now find the maximum current that we ever have coming through the base of the NPN transistor that has to deliver that 100 milliamps. That's the maximum current, which is 100 milliamps, divided by beta plus 1. And that's going to be approximately 2 milliamps. Notice in this example, in this part of the question, we've ignored the current that's going into the PMOS transistor, or the PNP transistor, because if you recall, it's going to be very, very small. It's going to be like 0.04 milliamps, and we can pretty much ignore it for this part of the analysis. So the maximum current that we're going to have going through the NMOS, or sorry, through the NPN transistor, the base current is going to be 2 milliamps. So the maximum current we'd ever expect to see here will be 2 milliamps this direction, because we have 100 milliamps going through here, and our beta is approximately equal to 50. But if this is 2 milliamps, we want to have at least 1 milliamp flowing through here. So that means this is 2. This must be then 3 milliamps. So we have to have 3 milliamps for the I bias to ensure that we always have at least 1 milliamp flowing through these diodes, and that they are never starved completely of current. So we have that our I bias must be 3 milliamps. Now we have that IQ is N times I bias. So we have that N was given as 3, if you recall, that was up here, the ratio of the area of the power transistors to the diodes. So we have that IQ must be 9 milliamps. So in this particular example, we found that our quiescent current is 9 milliamps, whereas our peak output current is 100 milliamps. So it's about 10% of our maximum current. So that's the extra quiescent, or the extra power that we've added on to this power amplifier. So if we look at just the power for the quiescent current, it's 2 times VCC, because it's plus 15 and minus 15 volts, times I sub Q, which is 9 milliamps, and so that works out to be 270 milliwatts. So we're constantly consuming 270 milliwatts, even if the output is always 0 and not driving any load. So in the case where the output is equal to 0, our emitter current will be 9 milliamps, as I mentioned, when we're not driving any load. The base current going into that NPN transistor will be that emitter current divided by beta plus 1, which works out to be about 180 microamps, or 0.18 milliamps. So that means that the current going through the diodes in that particular case is 3 milliamps, which is our nominal bias current, minus this 0.18, so it's actually 2.82 milliamps will be going through the diodes in that particular location. And that's when our output is equal to 0 volts. Now that we know what the current is through it, we can use our equation that the scale current of the diode over alpha is equal to 1/3 times 10 to the minus 13. This 1/3 comes about because we said that the power transistors have 10 to the minus 13 amps for IS over alpha, so the diodes themselves are 1/3 the size of that. So the IS of the diode is 1/3 of the IS of the power transistors. So now we can use that and solve for VBB, because we have our current, and we have the scale current for the diode itself, which we just solved over here. And that's times 2 VT times ln of this, and that works out to be VBB is equal to 1.26 volts. In the case that the output voltage is equal to 10 volts, as we saw before, in that particular case, the current through the diodes is going to be 1 milliamp. And we'd like to know the change in the VBB in that case. So in that case, we'll have that this will be 1 milliamp. So rather than having 2.82, it's reduced to 1 milliamp. And so we put in the same equation. We end up with a result of 1.21 volts. So in other words, when the output voltage is 0 volts, we have 1.26 for VBB. When the output voltage is 10 volts, we have 1.21 volts for VBB. If we do the opposite case and we say that the output voltage is now equal to minus 10 volts, then the NMOS transistor effectively has 0 current going through it. So there's all of the current is going through the diode, the two diode pair And that means that instead of having 1 milliamp, we now have 3 milliamp, which is almost exactly the same as we had here. And so we'll end up, when it's minus 10 volts, we'll end up with a voltage here, which is almost exactly the same as it was over in this case over here when we had 0. So whether we have 0 at the output or a negative voltage at the output, the VBB will remain the same at about 1.26 volts. Now let's say that we decided that that was a bit of a waste of power. We're wasting 270 milliwatts of power, so 9 milliamps of current, just for quiescent when our peak current is 100. So we're using about 10% of it as quiescent current. But let's say we want to reduce that down to 2 milliamps, so only 5% of our peak current would become our quiescent current. What would happen with the size of our diodes in that particular case? So we want to look at the same case, but we're reducing IQ to 2 milliamps. And we want to do the same thing. We want N to have a minimum current of 1 milliamp. So everything is very similar. We end up with 2 milliamps as we did before as the maximum current going through it. And we see that then the bias current is still 3 milliamps as before, so there's been no changes at all. But where we do see a change is now we look for the quiescent current is N times I bias. So N is equal to the quiescent current, which is 2 milliamps, divided by I bias, which is 3 milliamps. So we've made a quiescent current less than our nominal bias current, and that's equal to 2 over 3. So N is now even less than 1. So in this particular case, the area of our diodes are actually larger than our power transistors. They have to be 1.5 times larger than the area of the power transistors. And that's a significant a significant silicon area waste. You might ask why this isn't still just 1 as it was before. It's because we had this constraint that we always had a minimum current of 1 milliamp extra on top. So we had this one here, ID min, the current through those diodes would always have at least 1 milliamp through it and never go down to 0. If we let it go down to 0, then perhaps we'd get away with having an N which is equal in size, or an N approximately equal to 1, which would make the area of the diodes equal in size to the area of the power transistors. But that's still a significant waste of silicon area. So the way to get around this is to use something called a Vbe multiplier. So the purpose of using this Vbe multiplier is to be able to replace the two diodes that we had in this location with this circuit, and then use much less silicon area than you would have if you were using two diodes in that location, and be able to get a quiescent current which might be 2% the size of your maximum current flowing down through the power transistors. So what we have now is we have this part of the circuit here is called the Vbe multiplier. And the reason it's called that is if we look at the equations for that, start off and we'll assume that the base current going into this transistor is approximately 0. So this transistor can have a larger beta associated with it because it's not driving a lot of power. So it might have a beta of 100, in which case the base current going into it would be approximately equal to 0. So let's ignore that for the time being. So if that's true, then the current I sub R here is just equal to the voltage VBE1 divided by R1. And that because we're assuming this current is equal to 0. So we have I sub R is equal to VBE1 divided by R1. That's the current through that resistor. And that means that the voltage VBB will be IR, that same current, but times R1 plus R2. And since RIR is equal to VBE divided by R1, we have the VBB, this voltage, is the VBE1 times 1 plus R2 over R1. So we have the reason that it's called a Vbe multiplier is that the voltage across from here, from positive to negative, is equal to the VBE of Q1 times 1 plus R2 over R1. Sorry. Now, if we look at the currents through it, what we see is that the current through the collector of Q1, so the current IC1 here, is equal to this bias current, is equal to this bias current, subtracting this current, and subtracting this current. So we have IC1 is equal to that bias current minus the base current minus the current through those resistors. We also have the VBE1 is the thermal voltage times the ln of the collector current, IC1 that we just talked about, divided by the scale current of IS1, where IS1 is the scale current of that Vbe multiplier transistor. In a discrete design, you would just adjust R1 and R2 to get the obtained desired IQ that you want, perhaps through a potentiometer or so. Now, what we want to note here, though, is that as the current IBN changes, so we have a relationship here that is relating IC1 and I bias and IB1. What we'll see, though, is that this voltage here, this current, I sub R, does not change much. Because as IBN changes, IC1 will change. IC1 changing, though, doesn't change VBE very much. So VBE changes very slightly because of the exponential relationship with the transistor. So what we have then is that the IR remains essentially about constant. It doesn't change very much. So a delta change in the base current results in a change in the IC1 with the current through the resistor always remaining about constant, and therefore the VBE remaining roughly constant and not changing very much. So we can have a fairly large change in this current, and this voltage does not change too much because it's all absorbed by changing into this one here. So let's repeat the example that we had in the previous case, but we'll use now a Vbe multiplier, and we'll assume that the scale current of the Vbe multiplier transistor is 10 to the minus 14 amps. In other words, it's 1/10 the size of our power transistors. So we're saving a lot of error. We only have one of them, and it's 1/10 the size of the power transistor of Qn, or 1/10 the size of the power transistor of Qp. So it's quite a bit smaller than what we had before. We want to design now for a quiescent current of 2 milliamps. So we're not going to worry about the case where we had diodes which were very, very large because we have our Vbe multiplier here. So we can go for a quiescent current which is only 5% of, sorry, it's 2% of our maximum current, which is 100 milliamp. So it's 1/50th. So we have as before, the beta of the transistors were 50, and so we had our maximum current through the NPN transistors were 100 milliamps, so the maximum base current was 2 milliamps. So as before, our bias current then is always 1 milliamp higher than our maximum current that drives through, so our bias current is 3 milliamps as before. So this has not changed. This is still going to be equal to 3 milliamps. No change there, because the maximum we can ever have here is 2 milliamps as before. To design the quiescent current part of it, we note that the when our output voltage is 0, the base current now is going to be the quiescent current, which is 2 milliamps, which we've decided, divided by beta plus 1, and beta is equal to 50, so it's approximately 0.04 milliamps. So what we have then is that the in that particular case, if you recall, we said we have 3 milliamps through here. This is only going to be, this when Vout equals 0, this current is only going to be 0.04 milliamps. So a very small amount of current. So effectively, almost all this current plus this current will equal 3 milliamps, approximately. So we have that I sub R plus IC1 will equal our 3 milliamps, because it's just I bias minus IBN, and IBM is so small in this particular case when the output voltage is equal to 0. But now we need to decide, we have 3 milliamps that's going into the resistor and the transistor. So we have 3 milliamps going down. This plus this is 3 milliamps. How much should go to one side and how much should go to the other side? So we need to decide on our breakdown. Well, in the case when we have 2 milliamps happening from into the base current of the NPN transistor, then in that case we only get 1 milliamp that goes down through here. So in other words, when Vout is equal to 0, let me just get rid of this for a second. When this is equal to 0, then this plus this is equal to 3 milliamps. But in the case where this output voltage is not 0, but the output voltage is now 10 volts, then this becomes 2 milliamps. And so we have IR plus IC1 is now only equal to 1 milliamp. So that's the smallest we're ever going to see going down here is 1 milliamp. We know that IC1 is going to take most of the changes, but let's split them equally when it's 1 milliamp. So in this case here, we have the minimum is going to be 1 milliamp through it. So let's make 0.5 milliamps in each case. And that way, because our IR is not going to change very much, and I sub C1 will increase or decrease appropriately. So in the Vout case then, IR will remain about 0.5, but IC1 will be 2.5. So we have the two different cases, either IR plus IC1 is equal to 1 milliamp, in which case it's 0.5 and 0.5 for both, or ICR plus IC1 is equal to 3 milliamps, in which case it's still about 0.5 volts for IR and 2.5 volts for IC1. Now, since our quiescent current is 2 milliamps, we can then find our VBB voltage, and we know that's going to be 2 milliamps divided by our scale current for our power transistors, which is 10 to the minus 13, IS divided by alpha, and so that works out to be 1.19 volts. So we want to design our Vbe multiplier so that VBB is equal to 1.19 volts when we're in quiescent, when the output voltage is equal to 0 volts. So we have that IR is equal to, we had before that VBB was equal to IR, IR, the current through this, these two resistors is just equal to VBB divided by R1 plus R2. So that's equal to, it's 0.5 volts. We just said VBE was equal to 1.19, and that'll be divided by R1 plus R2. Right now we want to figure out what R1 plus R2 should be. What we found is that R1 plus R2 should equal 2.38 kiloohms. And that's again because we want 0.5 milliamps going down through it when we have a VBB voltage equal to 1.19 volts. So that's the first part, R1 plus R2, given by this. But we also have the VBE1, and again, when the output is equal to 0 volts, IC1 is equal to 2.5 milliamps. So VBE1 will be VT times the ln of 2.5 milliamps divided by 10 to the minus 14 amps, which is the IS over alpha for the Q1 transistor. So VBE1 will be 0.656 volts. We know that IR is also equal to VBE1 over R1. We have VBE1. We have IR. IR is equal to 0.5 milliamps. So we can then solve now for R1. R1 works out to be 1.31 kiloohms. We know what R1 plus R2 is. So R2 is just subtract those two. And finally, we have that R1 is 1.31 kiloohms and R2 is 1.07 kiloohms. So we do all that design at the case where Vout is equal to 0 volts. Now we look at what happens in the case when the output voltage equals 10 volts. In that case, as we saw before, the current through that transistor Q1 will now be equal to 0.5 milliamps. So when the output now becomes equal to 10 volts, this current here becomes equal to 100 milliamps divided by 50, because the beta of the transistor is 50. So this is 2 milliamps. This was 3 milliamps. So this is 1 milliamp going down through here. And we have 0.5 here and about 0.5 over here. So IC1 is equal to 0.5 milliamps. It says that VBE1, instead of being what we had before, we use this equation. We won't use the same equation, but we change IC1 here. We end up with the VBE is now 0.616 volts. So IR, rather than being 0.5 milliamps, is actually 0.47 milliamps. So it's changed by a small amount, which we expected, but did not change too much. And our VBB, is equal to VBE1, which is this value, times 1 plus R2 over R1. And so it becomes 1.12 volts. So if you recall before, it was 1.19, and now it's dropped to 1.12 when it goes to 10 volts as an output. Finally, when Vout goes to minus 10 volts, IC1 is still about 2.5 milliamps. So VBE1 is the same as it was before, and we still get 1.19, which is what we had in the previous case when Vout was equal to 0 volts. That ends this example, and thanks for watching.